So today I'm going to continue on with the discussion about weapons. And I'm going to take it's directly related to weapons, but a short diversion to talk a bit about the production of uranium-235 and plutonium for weapons, because I feel like that's important. I heard, this is obviously going to be important for your project. It's worth talking about some of the methods that are out there just generally. And then I'm going to go on to a discussion about nuclear testing. Now, I think this is particularly salient right now because under the new NPR, there's actually some discussion about accelerated testing. And I think it's important that you get a sense of what's involved in actually doing an intelligent test. A test that actually isn't just saber rattling, but provides some insight into how the device is working. So on that one, I'm going to do something a little bit different. I spent the weekend trying to think about good ways to talk about this and present it. I'm going to talk about the topic generally, but I am actually going to use a really excellent video that I found, which described the Castle series of tests. But I'm going to play that, and I'm going to periodically pause it and tell you what you're seeing and describe it in some greater detail. Okay? We'll see how this works. I think that in this kind of case, it's going to really work. So first of all, just to remind you where we were, in a modern two-stage weapon, you ping-pong back and forth several times between fusion and fission. You've got your primary with conventional explosives. That pushes the metal in. You've got an initiator and an injection of DT gas so that you get a flood of neutrons. Okay? So not only have you driven the rho R of the system up by compression, but you throw neutrons in at the correct time. Okay? That's how you really begin to get an efficient burn. Since you have the initiator that's going, here it is, and it uses fusion. This is the polonium-beryllium initiator. And you've got primary fission. The black material here is the fissile material going on. And you've got boost going on, which is giving you fusion from DT. And you've got then fission, because those neutrons from DT go through the assembled shell of plutonium or uranium. So you put all this together already at this point, we've got fusion and fission, and then more fusion and more fission. Then that energy is transferred to the secondary. This is really tricky to do. The goal of a lot of weapons is to maintain a good energy transfer, which is decoupled from any other transfer to the second part of the weapon, like from neutrons. But then you've got this larger device that you could not practically compress through the use of conventional explosives. That's the secondary. And you use this energy transfer from the primary to hit the secondary and drive a great compression, and you get a huge yield. The secondary typically can have fusion fuel in it, either deuterium and tritium, or, as you'll see in the case of Castle Bravo, lithium deuteride, which is solid fuel. A lot easier to do. The first thermonuclear weapon tested, does anybody know what it was? Probably you guys heard of it. Or thermonuclear device, I should say. Ivy Mike. Ivy Mike. Ivy Mike was not a weapon. Ivy Mike was a builder. Okay? It used cryogenic deuterium and tritium. This is not weaponized at all. Okay? It was huge. And really, the truth is, it's a big deal. It's very hard to have cryogenic deuterium and tritium and try to put that into a weapon. It's much easier to use the mixture of lithium deuteride and breed your own tritium. And that's what's used in most modern weapons. So you get another set of fusion and fission going on here. And so remember, this is where I said, this is the last slide we had before. You have fusion, fission, fusion, fission, fusion, fission. That's really what's happening. You're ping-ponging back and forth between these things. Okay? The fission reaction uses neutrons to moderate it and drive it. Fusion, really, you need to drive temperatures up. And so you need a lot of energy to get that done. You need compression. Okay? That's what's needed there. So there were a class of weapons that were, there was a class of weapons that were designed called enhanced radiation weapons. And sometimes some of these are referred to as neutron bombs, okay? There was a big hubbub when I was relatively young about the idea that the neutron bomb was a weapon that left buildings standing but killed people. Have you heard that expression before? Yeah, that's nonsense, okay? This is still a thermonuclear weapon. It kills people, it destroys buildings. What you can do, though, is you can design the weapon so that it produces less fallout. What part of the weapon is really responsible for fallout? What material in a weapon is responsible for fallout? Say it. Uranium or plutonium. It's the actinide. It's fission fragments. So if you go back here, in this, every time you see fission, that's a problem. So if you want to make a weapon that's enhanced in terms of radiation and damage, but doesn't leave as much fallout, you want to minimize fission. Now, we have not yet created a weapon that is fission-free. We have to have some fission going on, okay? But you can drive it down smaller and smaller. You use a thinner layer of actinide here. You don't need as much explosives. That's kind of a plus, okay? But you still do the same idea with an initiator DT fusion. And so no matter what, you're always going to have some primary fission going on here, and then a little bit more when the boost goes off. But now when you do the energy transfer to the secondary, you can design a secondary which is absent that black line, that black circle I have here. You can make it completely absent the uranium, okay, or the plutonium. If you do that, and you pack enough fuel into the secondary, you can get a huge yield. And really, what does the secondary produce in the end? Helium and neutrons. I think that's where the name neutron bomb came from. The fission produces neutrons too, okay? But these are fast neutrons. These are mostly 14 MeV neutrons that are coming out. And you need those neutrons for two reasons. In lithium deuteride, the neutron also breaks up the lithium to make it into tritium, okay? So these sorts of weapons would have less fallout, but they would have, they'd still be a big fiery ball of death. Okay, they're not, this definitely destroys buildings too. Okay, you can just lower that fallout ratio. So this would be important because a lot of our early scenarios in terms of nuclear war took place largely, frankly, in Germany. And they were our ally. And so you'd rather not salt their land with radioactivity for a long period of time. Okay, so there was a whole effort in this direction. But never to zero fission. We never got to that point. You could think of that as something of a holy grail or an unholy grail of weapons designers, was to get a weapon that had no fission at all. We just don't have that trick down. I am going to talk a bit about a facility that we have at Livermore called NIF, which in some sense is that dream come true. It's a pure fusion secondary, but you have to couple the entire NIF building with 192 lasers to it. But absent that issue, you can make this thing burn. Okay, so what I say here is that basically this last step of fission is gone. And that was a big deal. Because if you really want really high yields, you put a lot of uranium or plutonium around that. Remember that this thing is driven to compression by a primary. You can push a lot more metal if you use a nuclear weapon to set it off. Okay. So let's talk about sources of weapons material. And I'm going to start with U-235. So what I have here are plots of cross sections for neutron-induced capture and fission on U-235 on the top and U-238 on the bottom. You can see right away that U-235 is the only one that I could actually make a weapon directly out of, right? Look at that fission cross section. At low energies, it goes way up here. At thermal energies, it's around 584 bars, okay? That's not the case with U-238. U-238, with a zero energy neutron, does not fission. It captures that neutron. That's what it does instead. So remember, if you think about it as first you've got a hit, and then it makes a decision about what to happen. U-235, when that happens, mostly you fission. Remember that this is a log plot. You must be able to read log plots, okay? This is almost a factor of 10 difference. So what this is saying is down here at thermal energies, okay, room thermal energy, it's maybe not quite 10, but it's like 7 times bigger. The probability of fission is 7 times bigger than capture. Here in the uranium-238, capture is everything. Okay, you're like a part in 10 to the 6 down. Okay, so the only weapon, the only naturally occurring fissile isotope that I can produce a weapon out of, one that has fission at having a high cross section at low energy, is U-235. Okay, and you can see this then in this plot that I've reprised several times now. This is a plot as a function of the percentage of U-238 in the weapon, what the natural critical mass would be. So if I assemble a minimum surface area mass, which is a sphere, what it would look like for U-233 and for U-235. Okay, 233 is another isotope, and we're going to talk about that when I go into non-proliferation, but it's not a naturally occurring isotope in any meaningful quantities. Okay, so if you look at this, what you see is that you need infinite mass, effectively, for U-235 and U-238 when the concentration limit is about 5.4% U-235. Basically, you can't make this thing critical. There's no way to do it. Okay, so when the enrichment level is this low, you really can't have a sustained, ongoing supercritical assembly. You just can't do it. Okay, this is, of course, at natural density. If I push metal, things can happen. But I have to push a lot of meaningless metal. The 238 is not doing anything in order to get it there. Whereas if I get this thing up to at about 93%, you get to about 50 kilograms. Okay? So that's why U-235 is particularly valuable for this reason. But I've got to get it up to this extremely high enrichment level. That's challenging. Okay? And so, why? Well, fundamentally, it's challenging because U-235 and U-238 have the same chemistry. I can't like run some sort of chemical process, separate the two out, and then just keep the U-235. There is no chemical separation that can be done to separate isotopes. They have the same chemical property. The chemical property is dictated by the number of electrons. The number of electrons is dictated by the number of protons, and uranium is uranium. It's got 92 protons. That's it. So there are several approaches that can be used to enrich uranium. One of them is called gaseous diffusion, except it probably more properly should be called gaseous effusion. Okay, there's actually a difference from a thermodynamic standpoint. So the steps are simple. You react the uranium into uranium hexafluoride. Okay, uranium hexafluoride has this nice property that that you're able to melt it at 64 degrees centigrade. So you don't have to make this very hot. And you now have a gas which has uranium in it. In step 2, you infuse it through a membrane with holes in it that are approximately the size of the uranium hexafluoride molecules. This is the picture. Again, it's always lovely in stuff like this. There's great graphics on Wikipedia. You can always, or if not on Wikipedia, you can go click down into the sources. They really have a nice selection of things. So this is that process, okay? And when you do this, what you find is that if you have two different species, one of them is uranium-238 hexafluoride, the other is U-235 hexafluoride, that the effusion rate, the rate with which these things move through that surface, goes like the square root of the two masses. Note that this is flipped. Rate 1 over rate 2 is equal to the square root of mass 2 over mass 1. Okay? The lighter thing it fuses more quickly. That's basically what this is saying. Because the kinetic energy is shared between these particles, the lighter thing has a higher velocity. And the fact that it's a square root should be familiar to you because remember that kinetic energy equals 1/2 mv squared. And that's why you're seeing the square root here. Okay. So if you actually put in the masses for uranium-235 hexafluoride and uranium-238 hexafluoride, and you do this calculation, it works out that it's about 0.43% faster. And so you have a long tube, and you effuse through, and you look, like you open these holes, and you look some distance further down, after a certain amount of time, you will find that there's more U-235 out there. And then you can close the valve, you've now enriched it partially, and then you can repeat the process over and over again. This is gaseous diffusion or effusion. And this is probably one of the primary methods that would be used in many nations today to make enriched uranium. Okay? Now, approach number two, kind of lumping everything together here, I call them centrifuge techniques. Again, you still have to react uranium into uranium hexafluoride. Turns out that actually this is really a problem because fluorine, when it's in the presence of an alpha emitter, it can do an alpha in neutron out reaction. So fluorine is one isotope, alpha N. Fluorine, alpha N, okay, is a process that goes on anytime you bring uranium in contact with fluorine. And what's the problem with this? Look what just came out. The minute you react uranium into uranium hexafluoride, you have what's called a potential criticality situation. Because now you're creating neutrons, even if there's no fission going on. It turns out this cross-section, this is so incredibly important. We're spending millions of dollars to know what this thing looks like really well. Because you can have a situation where if you assemble enough high purity uranium in hexafluoride form, that it's generating a meaningful neutron field, which means that it could get towards criticality, especially if it got wet, because water is a good moderator. Okay? So we really need to know not just the cross-section for this reaction, we actually need to know the energy spectrum of the neutrons coming out. And that's very complicated because fluorines are light fluids. Okay? I was just at a conference where we had 2 days of people yelling at each other about this. I mean, it's an important thing to know. But, you know, you may hate it, but you gotta love it because this is the way you do enrichment. You create uranium hexafluoride. Okay? You then put that into a spinning zip centrifuge, which separates the heavier U-238 from the lighter U-235. And that should just be intuitively obvious to you. I spin these things, the heavier stuff moves out more. Okay? So I describe both of these actually as physical separation methods. We're taking advantage of the fact that there's a slight mass difference between these things. Okay? Yes?
That mass is really small.
It is really small. So you have to make lots of these centrifuges and they have to all be spinning. And what you do is you sample out from different radii from them and then set them to other centrifuges to run again. You keep in the same way that you would be doing that with the gaseous diffusion. You need many of these in a row. And they are spinning really fast. So the metal's got to be really strong. And it's actually not trivial to get metal that's able to do this. Okay? And so often a lot of non-proliferation effort focuses on trying to get rid of these enabling things, like the centrifuges. Okay, make sure that people can't get access to these sort of flawless metal tubes that can spin very fast and not explode. So, yes?
How fast do you spin?
You know, honestly, I don't know for sure, but it depends on the systems that you're using. They're generally designed close to a specification limit. Okay? I do know one system that I don't know if I can talk about it. Yes?
Why not use something else besides fluorine if you have that issue?
Oh, good question. Really, it's because the properties of UF6, that's 64 degrees centigrade, and otherwise chemically it's quite stable stuff. That's why you use it.
Okay.
The problem, by the way, I have the same problem with anything light. So when you remember the initiator is polonium beryllium. That's a light thing. We also have neutron sources that are plutonium carbon, which are called puke sources, or plutonium beryllium, or QB. There's lithium beryllium, americium lithium, AMLI. They're all these different, but they're all light. And whenever you put something light near a 5 or 6 MeV alpha emitter, like uranium, you have neutrons. You can't help it. They come out. And again, the spectrum is very important. The good news is the spectrum of those neutrons is pretty hard. So the cross sections aren't very high. But we actually still don't know that spectrum at the accuracy that's needed for most criticality applications. People who do criticality safety, there's a whole national program on this. It's extremely well-funded, well-supported program that's run largely by the Office of Naval Reactors. It's a really sophisticated program. And these folks are real, you know the expression belts and suspenders? They don't take chances, okay? And it shows, right? We don't have incidents with our naval reactors, okay, for that reason. But there's no better option. Bottom line is we're kind of stuck with this. Okay. So approach number 3 is laser separation. And I've got a fondness in my heart for this. A lot of the R&D for this was done at Livermore. And here the idea is that you use a laser to selectively, so here you form a uranium vapor. We're away from uranium hexafluoride, thank heavens. You use a tunable laser to selectively remove electrons from U-238 more efficiently than you do from U-235, more efficiently than you do from U-238. So it turns out, I said chemically these things are identical. That's basically true. But at the part per million level, there is small differences that you can pick apart. There are small isotope effects that are different. A laser is really good at doing that. You can tune the laser to sit at 1 energy. And that energy is closer to the U-235 ionization energy than the U-238 ionization energy. And so you can then use this to selectively break these things up. Because if you ionize it, then you can collect it on a charged plate. It's got now you create a positively charged plate you can collect on that. Okay. This is another method. This is pretty sophisticated. You need to have tunable dye lasers. They actually, and you need a lot of power if you want to do this in large scale. Okay, these are not things that you're doing in your garage easily. Approach number 4, I call electromagnetic separation. Okay, these are using devices called kyotrons, which were actually developed by E.O. Lawrence. So here what you do is you form again a uranium vapor. You then accelerate. I should put in an extra step here. You form this vapor into ions. You could do that actually just by heating the system up. Even that will happen. But then you accelerate these ions to high velocity with an electric field and run them through a magnetic field where they get bent. And it turns out that the lighter U-235 will be bent slightly more than the heavier U-238. So at the end point, you have a difference in physical location of where they're located. So kyotrons don't just work, by the way, for uranium. They're the primary way that we create isotopically enriched samples for medical isotope production. Or any time that you would need a separated isotope for an element that has several different stable isotopes, you do it using kyotrons. Okay. Right now, I think the primary producer of this stuff right now is Russia. Russia still has kyotrons running. We haven't in the US for some time, not in large scale. And I should point out that you can use this approach to separate lithium-6 and lithium-7 as well. 6 is the one that we tend to like to put in for dry thermonuclear fuel for weapons. Okay. But that's actually, this is the picture of that Lawrence submitted for kyotrons. I think that's kind of cool. Okay, any questions? That's U-235. Yes.
So is centrifuge the most common?
I don't know, like what's the most common is a good question. I think centrifuge is most commonly used in general. I don't know where other people are doing production. Gaseous diffusion is still used as well. There is no large-scale AVLIS, atomic vapor laser isotope separation capability in this country anymore. We have technical capabilities. You need to run a lot to create significant quantities of enriched material, okay? This is really large volumes, right? I mean, just think about it, it is 0.7%, natural uranium is 0.7% U-235. If you want to get 50 kilograms of that, it's got 50 divided by 0.07, okay? You need a lot, and you need to take that huge chunk, right, of whatever that is, 150 times 50, so that's like 1,500 times 5 is 7,500 kilograms of uranium, turn it into a vapor and run it as a beam through a magnet. good luck. That takes a long time. Centrifuges can scale up to that large size easily. So that's why I think it's one of the preferred methods. Okay. Yes?
If you go back like a couple of slides to the chart, yeah, that chart, it says on the bottom U238 percentage, but don't you think 93% to be U238?
That's correct, actually. That is the percentage of U238. Well, let me just show you what I'm doing here. This is supposed to be 7%.
Oh, okay.
So it is 93% U235. I should have been more clear about this. If you were to read on the bottom axis, that should have been 7%. But it's 93% U235, which is 7% U238. Okay?
And that means that.
That's why this is, I drew this by eye, by the way. I think that's not 7. Okay.
And that means that, so you need 93% of your mass to be U235 if you want the fission, to occur on stone.
Right, if you want to have a 50 kilogram sphere be critical, meaning that if I introduce in 1 neutron, I will shed 1 neutron, okay? If you want a sphere to be critical at 50 kilograms, you need to bring the U235 fraction up to 93%, or bring the U238 fraction down to 7%, okay? That's what that means. I think that picture was deceptive when I combined with it. Sorry about that. Okay. Are we good with this? I'm focusing a lot more on the uranium because, frankly, it's an easier material to make into a weapon. The fact that its cross-section is a little bit lower means that it's a little bit easier to deal with. It's also less horrifically toxic and chemically reactive. Okay? So from a proliferation standpoint, that's what we focus on. Yes?
You might have covered this already. Why, if neutrons in a weapon are fast, why can't you just have a fast reactor style weapon initiated with a fast neutron and deal with it?
Well, in essence, weapons are fast. They absolutely are. We don't moderate neutrons in a weapon. We do not. We moderate them in a reactor. Weapons do not attempt. Now, there is moderation that goes on because of inelastic scattering, okay? But we don't purposefully collide them with water, okay? The criticality safety issue I mentioned with uranium hexafluoride is because we store as uranium hexafluoride, and that might get wet. But our weapons are all fast.
Wouldn't the U238 also fission? Because it does fission for fast.
It will, but you'd have to introduce in a large number of these fast neutrons, okay? So you need to create them. So if I had a mole of, it's actually an interesting question. If I had a mole of fast neutrons right here, 1 gram, right? First of all, it'd be a crater where Berkeley was, okay? Because those neutrons would capture and they would release 8 MeV each, okay? It would literally, there'd be a huge explosion. That would be the end of class dismissed. If I was able to create a mole of fast neutrons in the center, absolutely, I don't need U235 at all. I'm good to go. Actually, even a fission spectrum will go pretty nicely, okay? The problem is because the effective threshold for U238 fission is about 1 MeV. The energetic threshold is 612 kilovolts, okay? So, it's a chicken egg thing. You need to create the fast neutrons in the first place, okay? And 14 is better. It gets a high enough energy in all of these actinides fission. By the way, if I had like 100 MeV neutrons, I could make a bomb out of lead. It would fission, absolutely. And it would, every bit is big a bang, basically. But I'd have to, how do I get that from a 100 MeV neutron factory, okay? We don't have that. We use boost to make 14 MeVs. Or we use lithium-6 deuteride in a 2-step process to create high-energy neutrons. So good question. So all weapons are fast.
Yeah.
They're designed. Okay. So PU-239. Here are the cross sections for PU-239 for the production of 239. This is U-238 N gamma. Here's the NF over here, very small. Remember what we said? That means the N gamma is big. And what happens then, how big? Well, at room temperature, it's about 3 barns. So what this means is that you can have this process where U-238 captures a neutron, it becomes U-239. That beta decays after 23.5 minutes, or half of the ones that you have decay after 23.5 minutes, to Neptunium-239. And that in turn, again, half of the beta decay after 2.36 days into Plutonium-239. So if you just sit uranium in a reactor, not a fast reactor, but just a normal thermal reactor, you're producing plutonium all the time. This is one of those, if you remember when I did the neutron economy figure, this is one of your neutron loss mechanisms. The uranium-238 is eating your neutrons, and it's producing Pu-239, which then is fissile, by the way. If you design a reactor, you have to take this into account. Over the course of time, your reactor fuel begins to turn itself into plutonium. And you then have to remove that plutonium, and also fission fragments, or else the criticality changes for the reactor. Reactor fuel gets spent. But if you do chemically process it, notice that these two beta decays, I turn the proton number from 92 to 93 to 94. Chemically, you can separate out plutonium. There's a number of processes that you can do. Purex is one of the most common ones, but in general, there are separation processes, chemical separation processes. As soon as this proton number differs, you can chemically separate. So reactors produce plutonium. That's what happens, especially thermal reactors where you have a lot of neutrons down here at low energy. They're constantly producing plutonium. So anybody who's got a reactor, it's a light water reactor, is making plutonium. And what we want to do is make sure that unless they're one of a few countries, that they do not reprocess the fuel, because that's the chemical separation. If they reprocess it, they can indeed gather the plutonium that was made, and you could use that for a weapon. Okay. As long as the plutonium is happily ensconced in a spent nuclear fuel rod, which will kill you if you try to work around it too long because of the radioactivity it's got, you're all right. But the minute you separate out the plutonium, you could have an issue. There are some fuels as well. Remember I showed you U-233 earlier? There's a way to make U-233 from thorium. And then it's kind of naturally resistant because the fuel really is deadly to work with afterwards. The plutonium you can, in principle, reprocess and pull the plutonium out and use it. You can put it together either for more reactors or for a weapon. There is one thing I would caution you about. I present this as this really neat picture, magically turning your uranium into plutonium, okay? And I've only been showing you curves for a couple of things, capture or fission, on a couple of things, just the major actors, 235, uranium, 238, uranium. So the reality is much more complex in a reactor, because the fuel that comes in is not pure. And if you can have one capture going on making U-239, why not have two? If you could capture on U-239 and make U-240, or you could capture on the Neptunium-239 and make Neptunium-240. That then beta decays, it makes Plutonium-240. And then that can capture neutrons. This is what real reaction networks look like. This is for a fast reactor. This is just focusing in on the uraniums on one side. Here's more of an extensive plutonium network with connecting up to the americiums. Because remember, beta decay is happening as well. Every one of the arrows that I showed here is either a decay process or, like in this case, going from Pu-242 to 243, that's a capture. Or over here, I can have Pu-243 going to Pu-242 by an end-to-end reaction. All of this is going on in a reactor, all the time, okay? Goes on in a weapon too, if the material is present, very quickly, okay? And we'll get back to that again in nuclear forensics. And virtually all of these cross-sections are unknown due to the short lifetimes of the targets. So some might argue, like in particular, reactions on U-239 are particularly interesting from a nuclear forensics perspective. It's a 23.4 minute activity. Yeah, I'm not making a target of that and running an experiment. Okay, this is a target that would be instantly ionizing itself into a plasma from its own beta decay. Right? So you can't measure these things. You have to come up with other ways to try to get at the reaction cross sections. We've spent a lot of time trying to do that. A good chunk of science-based stockpile stewardship was focused on trying to get on the nuclear physics side, getting at these cross sections. Okay. But it's also, this is a fast reactor network. The same thing matters there. Reactors and bombs have a lot in common, just reactors do it more slowly. But still, the same reactions are generally going on. Okay. I mean, we regularly make at a reactor, at a bridge, Californium-252. But nature basically gives us U-238. So think about that. You're having to capture 14 neutrons over the course of time. And we do that. We also saw, by the way, in tests, we put in plutonium-239 and got out Californium-252. Ivy might have that. So Ivy Mike just did all of this in a few shakes. Reactors take a few years. Okay. On to nuclear testing. So this is a good place to, should I stop? So just to understand the complexity that's involved in these things, okay? This has been, a lot of our focus has been trying to fill in these gaps. Okay. Not just for us in stewardship science, but this is also for nuclear reactor design. Okay. Testing. This is a nice figure to found away. Worldwide nuclear testing from 45 to 2018. Sad, but yes, we do have points out here now in 2018. And these are the main actors. And what you can see is that, for the most part, testing ended in the West around 1992. I find this kind of personally quite interesting. I got my PhD in '94, and I went to Livermore. Really, in what was it was this period of time in the country where we were just coming to grips with the fact that we probably were not going to continue testing. And Livermore had sort of emptied out. A lot of people took voluntary retirements, they moved on, and there was this idea that had been conceived by, I guess, principally Vic Weeks was one of the main components of this, is science-based stockpile stewardship. The idea being that you're going to start to get a scientific understanding of how the weapons were designed, as opposed to just building them and testing a hypothesis without having all the cross sections that you need, without having all the materials properties that you need, etc. Okay. So, so it's kind of interesting. And now we're petering down here relatively low. Perhaps we'll stay this way, perhaps we won't. So nuclear tests took place in different locations, okay? At or near ground level. That's what the initial testing program looked like. Okay, it seemed to be the obvious thing to do with a weapon. There are problems when you're near ground level. You interact a lot with the ground, which produces material that can then combine with your fission fragments and your unreacted actinides and create fallout. So ground level testing is a great way to sort of maximize your fallout, okay? Which was not the goal of testing. Testing wasn't trying to determine ways to make lots of fallout. From a military perspective, fallout is a mixed thing. It could have some tactical value in terms of area denial. You can keep people out, but really, mostly, it's a problem, okay? So there was also a great deal of testing that went on below ground. It was the majority of the tests that we did, and all the tests after 1963 were below ground that we performed. Okay. I think as a general principle, this continued. I think the French were the last Western country to perform testing, and that was a below ground test in New Caledonia. Okay. There you can, in principle, confine virtually all of the activity underground. But man, is this hard to deal with. You're talking about digging holes that are literally thousands of feet deep. And then you're setting a weapon off down there. And one of the principal things that you use to figure out how the weapon worked is to collect debris. But it's buried in the ground, okay? So you literally get all of this material. And basically, every element is present in soil, at least in Nevada, at some level. Okay, so it really makes it very challenging. Plus, if you want to look at any of the prompt signals of the weapon, you got to go deep underground. So it's definitely got problems to it. You can also detonate weapons just outside of the atmosphere. This is particularly useful if you're interested in testing the generation of electromagnetic pulses. So exo-atmospheric tests are interesting from a number of perspectives. They actually have much less destructive force in general, because there isn't much mass in the weapon that's going out. But one of the main ways that weapons interact and generate mass, which can explode things, is by picking up the material around them and throwing them up into a mushroom cloud. So it's less destructive, and you get this big EM pulse, because things remain charged longer in the vacuum space. And lastly, I realized I need to put this on barges at sea. That was an interesting approach that was used to lower fallout. Okay. Now, there's no way I can go over even a representative sampling of tests. We could go on for a very long time. Okay. So what I wanted to do was to look at a couple. I look at one test in particular, which was the largest thermonuclear test that we performed in the U.S. This is Castle Bravo. It was part of a 7-test shot series, the Castle series, and it was really America's entree into weaponized thermonuclear devices. So this was not Ivy Mike. Ivy Mike was a building with big cryogenic coolers to create DT. This was a dry fuel lithium-6 deuteride 2-staged weapon. Okay. A couple of neat pictures, by the way. I couldn't help myself. This is a picture of Castle Bravo before we went on. I'll go over this. This is a neat picture to show. One of the things that were done that didn't actually provide a lot of scientific insight, but provided interesting pictures. People used very, very fast cameras to capture pictures of the fireball in early evolution. This is a fireball from one of the Castle series, but not Bravo, I believe. This is at 1 millisecond after, well, actually, it's 1 millisecond after the end of anything meaningful. Okay, which means this is no longer critical. These things that shoot out, you know what they are? It's going to be. They're guide wires, that's right. So what happened, why does it happen?
Your movement of shock and material goes faster than your life?
It's actually not that the material is really not moving. What is moving faster than the material?
The shock.
No, the shock wave is the material.
Heat radiation.
You're getting closer, you're right, heat radiation. Photons, energetic photons and neutrons, by the way, at this distance, are way outstripping everything else. And they go out, they hit the guide wire, and literally what you're seeing here is that wire being turned to plasma. Okay? The fireball is coming behind it. The shock wave, that's a good point that you brought. Shock wave is an interesting concept. What is shock wave? Shock wave is matter that's moving. And there's not a lot of matter in a weapon. I mean, a few thousand pounds. Now, if I put it near the ground, I throw up a bunch of shock material from that. But otherwise, all I've got is radiant heat energy that's coming out, which is destructive enough. Okay. But this is what Castle Bravo looked like. This is the device, which was called Shrimp. And this is the sealed up end of the device. You can see there's definitely the length here. You're looking at the end. There's an aluminum casing around it. You're looking at the end that has the secondary in it. These things over here look like they're pipes holding it up. They're not. They're light pipes. So what would happen is, remember how this device goes off. The primary goes off. There's transfer through something called the channel to the secondary, and then the secondary goes off. Pipes, pipes, pipes. At every stage, you were looking at light generation. Okay. So, of course, these signals that are coming out, this is happening really fast. Remember that the multiplication rate of this thing is huge. Okay. So what you have to do is you look at these signals by sending the optical signal, turning it into electrons, and then putting it onto basically an oscilloscope screen, capturing this thing. Okay. And you look at time differences to see how the order of events occurred and if they match up with your model of how it should have worked. Okay. So the device was actually supported from below. These are all light pipes coming out of this thing. Okay. This is a measurement of where the fireball extent went for all the major weapons. A nice representative sampling here, at least. This is what the Minuteman I missile would look like, the W-59, 1 megaton device, about half a kilometer. This is the W-88 Peacekeeper, 350 kilotons. Batman, all of them you can see fit within this. So Castle Bravo, which is the big test you're going to see, was 1.5 megatons. It was 1.42 kilometers. The largest weapon ever was a 50 megaton weapon that the Russians exploded, which was the Tsar Bomba, and that was 2.3 kilometers. This just goes to show you, just to be clear, what cubing a number means. Going to very high yields, this is 50 megatons, right? And this is 350 kilotons. Doesn't seem like it's a very big, so this is 0.35 megatons. But remember that this is a sphere, and so the energy density goes like that's the sphere's radius cubed. So that's really a much larger area. Most modern nuclear attack plans call for multiple smaller missiles, warheads. Yes?
Is it possible to approximate the yield of the weapon that's definitely underground? Because it can't really take.
It's a good question. So we said possible to approximate the yield, you said? Yes. There's several ways. There is how much the Earth shook. There's seismic, okay? You also can look for debris, okay? And we'll go into that. You could look and see how many fission fragments you have. But the problem there is that all fission fragments are also elements that are stable potentially around as well. By the time you capture them, they beta decay to near stability. So what you end up having to do, this is actually very tricky, trying to back out from debris what this looks like. There's a trick that you can do. Okay, so the trick is you look at multi-order reactions. So what do I mean by that? So if I started with a bomb that has some uranium-238 in it, I'm going to undergo some captures and make that into U-239, which by the time I get to it is going to be plutonium-239. It's going to have undergone beta decay. But in a weapon, it won't just have stopped at plutonium-239. It's going to capture a neutron. When it was U-239, it will capture a neutron and become U-240. Then it'll capture another one and become 241, and maybe even 242. So if I look at now again, I'm not going to see those heavy uraniums, but I can see but what I know about their decay fragments is that they'll stay along the same mass chain. And I can look at ratios of masses. And that will tell me how many neutrons were hitting these things, and I can relate that to the yield, okay? But I need to know the cross-section. So you're caught in a catch-22. So often what happened is that we started with above-ground tests, interpreted information from them, then looked at radiochemical observables, and then looked down. Radiochemical observables were our main indicator of the yield. And you remember, you want to just not only know the yield, if it's a multi-stage weapon, you want to know the yield of the primary and the yield of the secondary, both of them. And so there were many tricks that were used, but radiochemistry was one of the first and foremost of it that was used. There are other hints that you can do as well, and I'll discuss some of those, like looking at the reaction history. And if you look at both of these things together, you can get a good sense about the yield as well.
But if you're not the one doing the testing, and you can't collect these,
you have to have a model. You need a model of the seismic transmission of the material that went off. And it's tricky. You can spoof the model, right? So it's challenging. There are other things too. You always get some shot at radiochemistry because some of the fragments that come off are xenon and krypton. And if you collect those, it's very hard to keep that in. They're noble gases. So the collection of noble gases can be used as well, potentially. But the bottom line is there's an uncertainty, especially if you're not there to look at it. Even if you are there to look at it, there's an uncertainty. These are good questions. Okay, let me look. It's a little bit further later than I thought. Let me show this movie. I think I'm going to do something a little different. I really want to get to this next part, but I want to show this movie. Let's wait till the end for the movie. I'm going to jump ahead. I want to show you more about the testing philosophy, and then we'll go back and see if we have time to do the movie. The philosophy of nuclear testing. So the first thing you have to understand about a nuclear weapon is that it's a massively integral system. What do I mean by that? It means that me as a physicist, I would never design something like this to get at underlying properties. I'm dependent on many, many different things. You need to know the nuclear physics. This is how the energy and the neutrons are produced. And I already told you I don't know most of the cross-sections of the spectrum directly. But it doesn't stop there. I need to know atomic and plasma physics. This is critical to that transfer from the primary to the secondary. Okay? How the energy from the primary is used to ignite the secondary. That's a whole field of atomic and plasma physics that I can't necessarily recreate in the lab. Material science, understanding how the uranium and plutonium respond to pressure, designing specialized materials with the right neutronics and the right physical properties. So a weapon depends on all of this. And people tend to get PhDs in one of them. Okay? So you have to have some way that you bring all of this information together and have a model that is built with input from experts. I'll be honest with you, this is not smooth. Until we actually manage to find a way to connect USB cables into our brains and directly transmit information, all of us are going to come with our own bias in terms of where our focus and interest is and what our view is. What the labs had to do was to try to get people together who had a relatively broad mindset. This is very different, by the way, from academia. My thesis advisor had a great line. She said, basically, the key to success in academia and science is to keep redoing your thesis experiment over and over again and pray that you never get it right. Okay? You just keep doing the same thing because you're now the world's expert in that one thing. That really would not work in the national laboratory system, the NNSA laboratory system. You have to bring people together and have there be a free exchange of ideas across disciplines. It's actually the exciting part about being at a place like Livermore or Los Alamos. You know, you get to actually talk a lot to people whose expertise is different than yours. But there's a big problem here. Because every one of these fields has uncertainties. And you can have errors in one piece of information or one part. They can either add to or be compensated for by another. So the fact that I have incomplete nuclear physics knowledge could, when put together with the incomplete knowledge of atomic or plasma physics or material science, could make a weapon be a dud. Or, as was the case in Castle Bravo, it actually turned out that that weapon worked a bit better than people expected. Okay? So really, this is very tricky to get this done. This piece of information is so incredibly important to understand that errors in one part can either add to or be compensated by another. We don't do this generally in academic research. We focus in one area. So as a result of this, I thought that nuclear weapons development used what I would call an engineering science approach. I actually used to just call this an engineering approach in a dismissive way. Okay, I don't do that anymore. Having come to respect a lot of engineers. What does it mean? What do I mean by this? Instead of trying to figure out all of the physics and chemistry and material science that goes into this, you start with a proven design. You adjust it slightly to test a new concept. Part and parcel of this is that you don't just look at yield. Yield is a tiny piece of this picture. You could get the right yield, and it's because one thing went up and one thing went down, and you haven't learned anything. And it may turn out that you got that right yield because the humidity was high that day. You have not learned anything, and you have no predictive capability. Military people want predictive capability. Okay? So what you have to have is a set of diagnostics. Nuclear, X-ray, and X-ray diagnostics. Why X-ray? Well, primarily what you see from the weapon is the outer shell, which is X-rays. The nuclear stuff is trickier. but it's what you actually need to see in order to get to the core. And then you're used to see if different components are performed as expected. And then you need some sort of a process of post-shock interpretation where the results are used to guide future testing. So all weapons testing had this sort of as its philosophy. So what would we do differently today? How would you do this? You guys, smart undergraduates and graduate students here at UC Berkeley, with all the resources that we have today, if I told you to go figure out a nuclear weapon, what would be the first thing you would do? To build one. How would you do it?
Go back to university.
And I would say nothing. No, but seriously, how would you do it? Come on, what do you do? Wikipedia, which would be flawed approach. But fair enough. Come on, what do you guys do? What do we teach you to do really in school? Sorry, not people who are not in the technical fields. What's the primary tool that you use? Literature? I don't think so. Nobody's going to say. What's that?
Gather information.
Gather information and conduct experiments. That's I like that. I feel really good. I feel valuable when you say that. But the truth is that's not what you're going to do. Come on, let's be honest. What are you all going to do? It's all sounding really good. So let's get rid of weapons for a minute. Let's say I want to design me a good widget. What's the first step that you're going to do in designing a widget?
Look at something else.
Maybe.
Ask what the prospective consumer of the widget would like to see and how much they're willing to pay.
Very business oriented. You can go and try to ask people about that. No, I mean, come on. What's sitting in front of all of you right now? What's in front of you? Computer. What are you going to do? You can try to look it up. Everyone looks information up.
Simulation.
Thank you. Come on. NCNT. JM. Right? Sorry. I'm speaking language that's hard to you guys. Yeah, Google, which in the end is going to be somebody's simulation. That's the truth. It's going to be somebody's simulation, right? We model the crap out of it. Because building things, performing experiments, as Bill very reasonably suggested, thank you, that keeps me in beer and pizza. Experiments are expensive, and when they're nuclear weapons tests, come on, this is really expensive, okay? Plus, you'll have to move out of Berkeley, because nobody will want you around anymore. You will model it. This is what we do now. You have to remember that all science and all research endeavors are being done by people living in their social and cultural milieu. That's where you are. You're going to simulate this thing. Most of what we do in our department now is simulation, right? That's why I was going up to Marissa. And I'm like, Marissa, come on. Okay. It's true. It's simulation. They didn't have this, right? When they were doing testing, computers were human, okay? Not humans ran computers, you know, they were humans, okay? They had some other computers, but the truth is they were very limited in terms of what they could do this way. We're a lot better off, right? Right? No. Actually, what we've done is we've changed the way that the field is done because of the invention and ever-growing capability of computers. But even the best computers can make you immune to those sorts of errors that I was describing before. At the end of the day, your simulation is only as good as the model. And the model is only as good as your knowledge of the underlying physical and chemical properties. Reality doesn't care about your beautiful picture that you generated on a computer. Even if it has fractal beauty to it and looks intuitively right to you. One of the professors in our department who actually I believe Marissa's worked with, Rachel Stabile, showed me this beautiful picture of a neutron transport model result. And I looked at it and I was like, wow, this is really cool. You could see there were these instability-like structures that you would expect to see in nature. And she said, yeah, it's all wrong. Okay. But it looked beautiful. My aesthetics were pleased, okay? Let me give you an example of this, because this is something you need to carry going forward. This is an example. This was work that was done by Eric Boge, another very bright French weapons scientist from CEA Denham. Eric Boge published this paper where what he did is the following. There's these things called critical assemblies. Easy for you to now understand. Basically, it is a ball of material that is a critical mass. Okay? He looked in particular at one of these called Jezebel, which was a critical assembly of plutonium-239. And we modeled Jezebel using MCNP. Okay, that is a code that we use in nuclear engineering to model these things. Okay, the French did it as well using MCNP, but MCNP, Monte Carlo neutron photon, MCNP uses cross-section data, and cross-section data is made by humans. In America, we call this the Evaluated Nuclear Data File, NDEF, version V8 Beta 5 just came out. It's like 10 years between new versions. BRC09 is the database that the French use, and by the way, none of this is classified, it's all out there. And in both cases, when we modeled this, we came up with the fact that, are you waiting for it? Jezebel is a critical assembly. The K effective is 1.00083 plus or minus 11, or 1.00060 plus or minus 12. If you saturate these areas, they overlap. Everyone's happy, right? Well, of course, we knew that Jezebel was a critical assembly. We've assembled this at great pain and saw that it's critical. Okay. But is this reality? That's a picture of Jezebel. Jezebel's gone, by the way. It had an uncontrolled scram. Okay. A small, very short criticality excursion. So Eric did this neat thing where he went in and he took one cross section. He modeled the whole thing using NDEF. Then he pulled one cross-section out from NDEF and put in a cross-section from BRC09 and redid the calculation. So, and then he looked at how much the criticality K-effective parameter changed. First, he changed the fission cross-section out. And he saw that making that change lowered the criticality by 0.122%. Okay? That's because French and American reaction evaluators looking at the same experimental data came up with slightly different fission cross-sections. Okay? If you go in and you only change the cross-section, you just change the spectrum of the neutrons coming out, it also goes negative by about 0.16%. By changing out the neutron capture cross-sections, it went more critical by 0.275%. Elastic made it less critical by 0.638%. N2N changed it by 0.14%, and inelastic changed it by positive 0.522%. Okay? So this swapping of one cross-section for another produced small changes overall in the K effective for cross-sections where we think we know the values well, like fission, but where we don't know them well, like elastic and inelastic scattering, they produce big differences because the science is done by humans. And humans are guided by their observation. And what we saw here, we don't really know these cross-sections well. So we had big uncertainties in them. Now you're looking at this, you're saying, Lee, why are you obsessing? 0.522%, is that really a big deal? I'm going to remind you what a change in K effective means. What this means, like with this inelastic scattering cross-section, is that if I go from one cross-section value to another, every cycle through, if I put in one neutron, I will get 1.00522 neutrons out. Doesn't sound like much. But Jezebel was only about this far across. And neutrons traverse that in about how long? Do you remember how long it takes for a neutron to traverse a reasonable distance? A shade. That's right. Right? 10 nanoseconds. What does this mean? If you have this big of a change in the cross-section for real, in 1 millisecond, Jezebel's yield would go up by 2 million-fold. Okay? This is why people who do criticality studies are very concerned about numbers this small. In fact, the nuclear engineers will tell you we never would talk about 0.522%. That's not, we talk about PCM, percent yield, thousandths of a percent. If you get beyond 100 PCM uncertainty, you don't feel good, okay? Because so quickly the neutrons propagate through a fast system. So I want to bring this up because I want you, and keep in mind, this is just the nuclear physics that we've had, okay? So this is a good time. I'm going to go back and show you the movie, and I'm going to bring this around to a point that we're going to need to think about here. We're still, nuclear weapons testing was done in a fairly organized way with people who were quite aware of the fact that there was lots of compensating errors and that there wasn't time to know all of the microphysics right. There was no effort to go out and do lots and lots of cross-section measurements or push metal in different ways or try to do experiments with ion traps to learn more about atomic physics and plasma physics. No. We were in a race for, in their opinion, the nation's survival with the Russians. So we had to just keep trying different things and moving it forward with an engineering type approach, okay? That approach, though, was quite clever and quite well done, actually, overall. And that's where we get to this video that I was going to show you. This is where I'm going to end the classes. I'm going to show a bit of this, and we'll go forward. Okay? And I think I've got the volume up such that this should actually be running. Sanitized, it's clean. You can actually see where they've removed some of the stuff. All of a sudden, this language is cut off. Okay. There's pretty dramatic 1950s era music at points. So this was 7.
Another accumulation of men, of machines, another meeting of ships and aircraft and troops. Here was the best of physics, of metallurgy, of electronics.
Listen to that. They knew what they were doing, that they were pulling together all of these parts.
During the months after the historic Mike detonation, preparations for a new series of tests to solve the problems of a deliverable megaton weapon went ahead at an accelerated pace throughout the country.
So remember, Mike was a building. We weren't going to drop a building on Russia, okay? You needed to make it deliverable.
Operation Castle became a reality and is now successfully concluded. The report which follows is a summation of what occurred at the Pacific Proving Grounds during that operation in 1954. Here to lead off this record is General Clarkson, Task Force Commander.
Operation Castle was concluded on the 14th of May, 1954. Castle was an all-thermonuclear test, a test basically of devices in the megaton range. We feel that the report of this important test should give the failures as well as the successes.
That's amazing. I got to tell you that when I worked at the National Ignition Facility, I would have loved to have had this guy somehow running the science program. Okay? You have to give a report of the failures as well as the successes. That's very important.
Should reflect the changes in thinking that occurred during the test. We hope this treatment will help you understand the problems that we experienced during the course of the operation. This program encompassed then 3 shots on land and 4 shots on burden. Our main base camp on Bikini was located in the same island complex. The firing station to be used on all Bikini shots was located on NU Island. Barry and Eniwetok Islands on Eniwetok Atoll again functioned as the center of land-based operations. This then was the weapons schedule and the operational plan for Castle of March 1st.
Just to be clear, they shipped like the entirety of a national laboratory out into the middle of the Pacific. Okay.
Perry Island, Enuitake Atoll. This is the third time this island has been used as the headquarters for Pacific Task Force. For this operation, a weapons assembly area was constructed at the southern tip of this valuable piece of real estate. This is the first time on any operation that weapons were assembled on Perry and then moved out to the firing site. Weapon development would be impossible without diagnostic instrumentation.
Listen to that. Only an idiot would say that you're going to detonate a weapon without diagnostic information. That's the truth. This is the building.
But such instrumentation is expensive, very expensive at this distance from home.
Another acknowledgement of what's required here. So the weapon sits here, and you saw these long tubes that are going out. I think he's going to describe them again.
For this reason, extensive.
Oh, and these devices over here as well. We'll talk about them later. These things here, we're looking at gamma output.
Instrumentation was limited to a few shots, and each diagnostic experiment was carefully considered before being included in the program. This instrumentation, while more elaborate than that of other shots, is representative of the...
Those are neutron time of flight lines. For those of you who do nuclear physics experiments, we have one of them up the hill. We're 7 meters long. I don't know how many miles that thing is, okay? But you need a pretty high flux to be able to differentiate things from that far away. Sorry, technical detail here.
Type of diagnostic studies made. Recorders to read the yield of the primary bomb from its rate of neutron multiplication. Cloud sampling for radiochemical determination of fission yield.
And that was important. Notice he says it right there, okay? This is how you determine fission yield, radiochemical sampling, okay? By the way, one of the things you guys take in nuclear engineering, they take this course where they play with all these really cool gamma ray detectors called germanium detectors. When they're looking at that, they allow each pulse time to come in, the signals to be processed, et cetera, and everything is separated. In a weapon, everything comes at once, okay? We don't even really teach students any longer how to deal with signals of that sort. Okay? It's different, it's called current mode. So really, the way you know how to learn how to do stuff like this is at the labs.
And to assist in determination of total yield. High-speed cameras and photo towers for polar fire photography to indicate total yield of the device. Scopes recording electromagnetic radiation and cameras, both to obtain the time interval between primary and secondary bomb detonations. Other cameras to look directly into the open door of the cab. A great mass of information was gathered as a result of an array of 12 evacuated pipes. These pipes are like peepholes, looking at portions of the weapon's case.
So that's all, these are all time of flight and gamma ray lines. They were evacuated so that they wouldn't get selective absorption from nitrogen and oxygen in the atmosphere. So these were not just mile-long things, they were pumped down.
To pick up gamma and neutron emission from many stages of the reaction. Starting at H-48 hours, all personnel at Bikini Atoll were evacuated from the scattered islands and moved aboard task force ships. The only men to remain were the members of the firing party, protected in their bunker on Enu Island. Once more, for the first time since Operation Crossroad in 1946, Bikini took its place in the story of atomic testing. The date was March 1, 1954.
This photograph was taken from an airplane at 50 miles. The width of the fireball at this time, about 3 seconds after detonation, was 4 miles.
So it moved out 4 miles in 3 seconds, okay? There's 3,600 seconds in an hour, so that's 1,200 times 4. The fireball itself was moving at 4,800 miles per hour. Okay, speed of sound is about 700 miles per hour. So you'd be hit by this thing, you wouldn't hear it coming.
The frame size of the picture is 6 by 8 miles.
So just to let you know, in the real debrief for this thing, during some of these breaks where there's quiet, they're going down and telling you what those different diagnostics we're seeing. Okay. So there's a lot of other information you don't hear. You see pictures of the fireball. Yeah.
10 tons. The tremendous yield resulted in a serious fallout situation at Bikini and certain other atolls downwind from ground zero. This was the forecast wind direction. The actual wind was in this direction, some 10 degrees less favorable than forecast. Even so, the winds were within the area of acceptable fallout. However, the unexpected high yield had caused significant fallout to occur on Roger Atoll, 110 miles distant, on Roger 150 miles from Bikini, and on Uterik, 280 miles out. After the natives were evacuated, radiation survey teams were flown back to the exposed atoll, where studies were made and water and soil samples taken. Rongelat had a native population of 82. Evacuation was carried out on the second morning after the shock. Rongerik had no native population, but was occupied by 28 men of the task force. 8 men were evacuated by air at H plus 28 hours, and the remaining men soon after. Uterik had 150 natives, and they were also evacuated, although radiation levels here were relatively light. The removal of personnel from the contaminated atolls was done mainly by destroyers. These destroyers were attached to the task force primarily for security purposes, but were easily adapted for use as evacuation vessels. All of those exposed were taken to Kwajalein, where complete physical examinations were carried out. Every effort was made to assure their comfort and well-being. Fallout on Bikini temporarily rendered that atoll unusable. 25 hours per hour was recorded on Enum, our port of entry.
We're going to talk about what R means here. It's many things.
On NU, the site of our control station, 35 hours per hour was recorded. Hundreds of Roentgens per hour were measured on Ammon and Bikini Islands.
That would give you a lethal dose, as you'll see in a few hours.
Even if radiation had not been a factor, blast damage on Ammon was considerable.
And so here's the point that I was making before. You're dead anyway, okay? You're that close, you're getting radiation from a megaton level weapon. You're dead anyway.
It would have taken a sizable effort to make that island again usable as a base camp. The ground shock and fallout experienced by our firing party on NU forced us to give up the idea of a manned station. The necessary electronic systems were installed on the USS Estes to permit firing remotely by radio. The possibility of further damage to previously prepared shot sites at Bikini caused us to change our schedule at this point.
Back in the States, at about the same time, Castle.
Let's see if they have. The bottom line is, let me show some of this.
As on previous tests, the armed forces took advantage of the Castle series to broaden their knowledge of the effects produced by high-yield weapons. As an example, there has been much uncertainty in specifying the minimum safe distance for aircraft delivering high-yield weapons. Blast and thermal effects were measured on B-36 and B-47 aircraft, positioned so that some damage was expected. This data will help us to specify the yield at which parachute drops are required for delaying a detonation, as well as providing us with answers to many questions which arise when positioning for multiple drops is considered. The whole picture of fallout contamination becomes of increasing importance with high-yield weapons. In one program, drone ships were sent into fallout areas to evaluate the worth of a washdown system for ship decontamination.
Look what they're doing here. This is an important point to know about decontamination. They're basically washing the surface of the ship with water. The primary way to protect yourself against fallout radiation is wash it away. That's the whole point. So a lot of it comes down to that.
We found we could measure fallout even in large ocean areas by making aerial surveys using extremely sensitive radiation detection equipment and with surface craft such as tugs and destroyers. As a result of these measurements, we were able to document for the first time fallout data from high-yield detonations. It is now known that fallout from the larger castle shots blanketed areas of more than 5,000 square miles with radioactive material that would have been lethal to unprotected personnel.
And so that is because everybody stuck in that area wouldn't have any protection, right? It's assuming that they wouldn't be able to wash themselves off and get clear of the fallout. Okay. And that's really, I think this is where I'm going to stop today on this, because we're going to talk later about that radiation impact and effect directly. And then we're going to look specifically at another massively integral system that uses some of the same tools and techniques of testing. And that's it. Thank you.